Welcome back everyone. In this lecture we will complete the Burnside theorem by proving the key result that we left over in the last class. So, let me first state the result and then we will go through the proof. So, here is the result. So, as before we just assume that G to be a finite group of order n and C be a conjugacy class of G with the order let us say H. So, we take G to be finite group of order n and C a conjugacy class of order let us say H. So, that is the cardinality of C. Suppose that we have this irreducible representation, let us call it phi. So, this is a irreducible representation let us say of degree d, and we make the assumption that the GCD between H and D they are relative prime. So, with this assumption then we have the following conclusion. So, either we have that this phi g is going to be scalar times identity for all elements G in C. So, you have some scalar lambda in C star such that this phi g is lambda times identity for all C in for all G in C, or we can actually conclude that the trace of phi g is going to be 0 for all G in C. So, if we take the character value, so that is going to be on G will be 0 for all G in C. So, only one of this will happen. So, whenever we consider irreducible representation such that the degree of representation and the number of elements in the conjugacy class they are relative prime. So, this is actually an important result that was used proving this Burnside's PQ theorem. So, let us actually go through a proof of this. So, first we will start with making some important observations. So, let us look at the statement 1 and then statement 2. So, we can see that the statement 1 asserts that phi g is supposed to be scalar matrix for all G in C. Since the elements of the conjugacy classes they are all conjugate, in particularly if we take another element G dash from C, then phi g and phi g dash both are going to be conjugate matrices, and the scalar conjugate of a scalar must be again scalar. So, that would imply that if we have phi g equal to lambda times identity for some G in C. So, then we will have phi g equal to lambda identity for all G in C. So, let me just write down all the observations. So, we can see that suppose we have phi g equal to lambda times identity for some G in C. So, then we can conclude that phi g dash equal to lambda times identity for all G in C. So, the reason being, so if I take a scalar matrix lambda times identity, so then if I conjugate with any other matrix let us say capital A, then it is immediate that you get back lambda times identity for all A invertible matrices. So, that means the conjugate of this phi g is going to be again lambda times identity, but since all elements of this phi g dash and phi g for any G dash in C they are going to be conjugate, we get this result. So, now what is about the second statement? The second statement again we can use that the character is nothing but a class function, and since we are considering only a class corresponding to G in C. So, once we have chi phi of G is 0 for some G in C, that would imply that chi phi is 0 on entire C. So, again that is also true. So, if there exists G in C such that chi phi of G is 0, so then we would have that chi phi of G dash is 0 for all G dash in C. So, with these key observations we can see that the theorem is equivalent to proving the following. So, if we assume there exist phi G such that it is not a scalar matrix, so then that would imply that this chi phi of G is 0. So, that is actually enough to prove. So, let me make that very precise. So, the following observations tells us that it suffices to show that if phi G is not equal to scalar times identity for some G in C, so then we conclude that chi phi of G must be 0. So, we are going to prove this statement, which is equivalent to the statement in the result. Okay. So, how do we actually go about proving this? So, we have to make some observation about this value chi phi of G. So, let us recall some of the observations that already we made. So, since we are actually working with a finite group, so recall that. So, given G in G and suppose the group has order n, then we know that G power n must be identity. So, that would imply that this phi G power n is going to be identity operator on V. So, that means all the eigenvalues of phi G, they are nothing but some n roots of unity. So, if I from this we can conclude that phi G is nothing but diagonalizable. So, not only that, so if I call this lambda 1 etcetera lambda 2 lambda d to be eigenvalues of phi G, then they are all actually nth roots of unity. So, they belongs to those Z in C such that Z power n is identity. So, these are all the, let us say, eigenvalues of phi G. Okay. So, this is something we made this observation earlier. So, that is what we are going to use it again. So, this observation tells us that the trace of phi G, which is the value of chi phi of G. So, this is exactly the trace of phi G is the sum of these nth roots of unity. So, lambda 1 plus etcetera plus lambda d. Since all nth roots of unity they are algebraic numbers, then that actually implies that this chi phi of G is nothing but an algebraic number. So, not only that we also proved something about this ratio. So, if we take this ratio h of chi phi G divided by d, and we proved that this is also an algebraic integer. Okay. So, we are going to use these facts now. Now, since we have this GCD between h and d, they are 1. So, since the GCD between h and d they are 1. So, we can find some integers j and k such that, so we can write 1 as integral linear combination of this h and d using j and k. So, j d plus k h is going to be exactly 1. So, now we just set this alpha, which is exactly chi phi of g divided by d, and we are going to claim that this is also going to be an algebraic integer. So, we already know, so this number is indeed an algebraic integer, but we are going to actually drop this h and then say that chi phi of g divided by d is also an algebraic integer with the assumption that the GCD between h and d is 1. So, how do we prove this? So, we can just use that fact 1 can be written as j d plus k h. So, now note that, so this is exactly 1 times chi phi of g. So, we just rewrite this 1 as j d plus k h chi phi of g divided by d. So, then alpha becomes exactly equal to j times chi phi of g plus k times h chi phi of g divided by d. Now, note that, so this element is again an algebraic integer as being integral multiple of an algebraic integer, and again this is also an algebraic integer because it is again integral multiple of algebraic integer. Their sum is also again going to be algebraic integer. That would imply that alpha is an algebraic integer. So, now we have this alpha being algebraic integer. So, now since we have assumed that this phi g is not a scalar matrix. Okay. So, maybe let me actually start with that. So, we fix g in C such that phi g is not a scalar matrix, and we want to prove from this that the character value is indeed 0. The character value is indeed 0. So, let us assume this. So, since we have assumed that phi g is actually not a scalar matrix, so that would immediately imply that all the eigenvalues of phi g, they are not supposed to be same. So, note that with respect to some basis, so phi g, the matrix of phi g is going to look like this lambda 1 etcetera lambda d. So, now since this is not a scalar, and that would imply that not all lambdas are equal. So, there exists some I not equal to j such that lambda I is different from lambda j. So, this is already there. Okay. So, now look at the value of this chi phi of g. So, what we can actually conclude, the chi phi of g is going to be exactly the trace of phi g. So, which is exactly lambda 1 plus etcetera plus lambda d. Now, since lambdas are actually not all of them are equal, so that would imply that the absolute value of chi phi of g is going to be strictly less than 1. So, indeed the absolute value of this chi g is exactly the absolute value of lambda 1 plus etcetera plus lambda d. Now, using triangle inequality, you can see that this is exactly less than or equal to summation mod lambda I range from 1 to d. Since lambda i's are all nth roots of unity, so the mod lambda I must be 1. So, this is going to give us exactly d. Now, from elementary analysis, we know that this inequality becomes strict in equality if and only if all the lambdas are equal. So, maybe I will leave it as exercise. So, prove that this inequality becomes equality. So, lambda 1 plus etcetera plus lambda d equal to d if and only if lambda I equal to lambda j for all I j between 1 to d. So, that means we can immediately conclude that the absolute value chi phi of g, this is going to be strictly less than d. So, that immediately implies that this alpha, which is by definition chi phi of g divided by d. So, the absolute value of this is strictly less than 1. So, this is what we are getting from this observation. So, now we want to say that this alpha is 0. So, that is our ultimate claim. So, we claim that alpha is indeed 0. So, to prove this what we are going to do, we are going to use little bit of Galois theory. So, maybe I will just recall it here. So, recall. So, you can already see that alpha is nothing but, so d times alpha is nothing but sum of these eigenvalues lambda I, which are nothing but roots of unity. So, in particularly, so alpha lies in this splitting field of this x power n minus 1. So, what we can do, we can take the splitting field. So, indeed the splitting field is given by, it is extension of q, which is generated by this nth primitive root of unity. So, we can take this omega n to be nth roots of nth primitive root of unity. So, this omega n is nothing but, for example, we can fix this nth primitive root to be 2 pi I divided by n. So, then it is a fact from Galois theory that this is indeed a finite extension of q. So, basically this q of omega 1. So, this is a finite extension and the degree of this extension is nothing but pi of n, where pi of n is nothing but Euler phi function. So, which counts the number of L's, which is actually less than or equal to n, such that the GCD between L and n equal to 1. So, it counts the number of elements between 1 and n which are relatively prime to n, such that the GCD between L and n is exactly 1. So, the degree, that means the dimension of this extension q of omega 1 over q is nothing but pi of n. And not only that, this is also called a cyclotemic extension, and the Galois group of this is very explicitly known. And since this is indeed a splitting field of this, this is a splitting field of this polynomial x power n minus 1 over q, and since we are working over characteristic 0. So, this is indeed a Galois extension. So, this is indeed Galois extension, and the Galois group, which is the automorphism group of this q power omega 1, which fixes q. So, let me just recall the Galois group, Galois q of omega n over q is nothing but those automorphisms of q of omega n, such that q restricted to rational numbers is nothing but identity on rational numbers. And what we know about this Galois group, the Galois group indeed isomorphic to the units in z modulo n h. So, maybe you can take it as exercise, the Galois group of this q omega n over q is naturally isomorphic to z modulo n z star. So, the cardinality of this group known to be given by pi of n. Okay. So, where are we going to use this this Galois theory? So, we have the following basic facts from field theory. So, let me just recall them, and then we can see that if we want to prove some algebraic integer as a rational number, then we can actually use some information about this Galois extension. So, let me actually make those observations aside. So, since these are all some standard facts from Galois theory, so I am not going to prove it, maybe I can check one or two statements if it is necessary. So, here are some facts from Galois theory. So, let us call gamma to be the Galois group of this q of omega n over q, and as we observed, this is actually indeed the units in this ring z modulo n z. So, now we have the following important observation. So, if we take beta to be an element in this extension. So, since this is finite extension, this is also given by this bracket. So, then we can immediately see that. So, this beta is a rational number if and only if this beta is fixed by all elements of gamma. So, sigma of beta is exactly equal to beta for all beta in gamma. So, the strategy is that we want to prove this alpha is indeed 0. So, what are we going to prove? That since alpha is already an algebraic integer. So, we have actually observed that alpha is an algebraic integer. So, we will use Galois theory to prove that it is indeed in the intersection of algebraic integer and rational numbers. But we already know that A intersection Q is nothing but Z. So, that would actually makes alpha to be an integer. Since the absolute value of this alpha is indeed less than 1, that actually immediately implies that alpha must be 0, because there is no non-zero integer whose absolute value is strictly less than 1. So, that is the strategy. So, that is what we are going to use. So, in particularly in order to prove that alpha is a rational number, we will actually prove that alpha is indeed fixed by all sigma in gamma. Okay. So, now so how do we actually come up with some element that is already guaranteed to be a rational number. So, suppose if we actually take beta from this extension field. So, then we can at least immediately say that the sum of sigma beta, where sigma runs over gamma, and the product of sigma of beta, sigma comes from gamma, both are elements of Q, because both will be invariant under gamma. So, in particularly these elements guaranteed to be rational numbers. So, now we can also say something about the roots of given polynomial over rational numbers. So, here is the third fact. So, let us fix some polynomial p of x inside q of x. So, that means it is a polynomial over q whose coefficients are rational numbers, and let us fix some beta from this extension and assume that it is root of this polynomial p of x. So, now what we can conclude, if we take any sigma beta, so that is also going to be root for this polynomial for all sigma in gamma, and this is something very basic from field theory. So, here is a proof. So, if I take p of x to be some a k x power k plus etcetera plus a 1 x plus a naught with all these coefficients a i's from rationals, then from this you can actually see that if you make this sigma to act on this p x, then that will leave p x invariant. So, sigma p x is exactly sigma a k x power k plus etcetera plus sigma a 1 x plus sigma a naught, which is exactly equal to, because sigma restricted to rationals is nothing but identity on rationals. So, that would imply that this is exactly equal to p of x. So, in particularly if we take sigma p of beta, so that is going to be again 0, because this is exactly equal to p of beta. And what is sigma of p beta? That is exactly p of sigma beta. So, that would imply that sigma beta is again a root for this polynomial p of x. Okay. So, now if you have beta to be nth root of unity, then what we can say? We can also say that sigma beta is also an nth root of unity. So, as a corollary, so we get the following: if beta is a nth root of unity, so then we can conclude that sigma beta is also a nth root of unity, and this is true for all sigma in gamma. So, now from this again we can conclude that if you have beta to be an algebraic integer, so if beta is an algebraic integer which is also happen to be in the extension, and let us say sigma to be some element in gamma. So, then we can conclude that sigma of beta is again an algebraic integer. So, this is also a corollary of 3. So, because if beta is actually an algebraic integer, then it satisfies a monic integral polynomial. So, in particularly sigma fixes q. So, if sigma fixes actually integers. So, that would imply that this sigma beta is also an algebraic integer. So, these are all some easy statements to verify. Maybe I will leave it to you to check. So, now how are we going to use these facts in order to prove our result? So, we already observed that this chi phi of g is nothing but the sum of these eigenvalues of phi g. So, being this implies that the absolute value of alpha, which is exactly the absolute value of chi phi of g divided by d, is strictly less than 1, as chi phi of g, the absolute value is strictly less than d. So, now what we are going to claim? We are going to claim that this alpha is indeed actually belongs to q as well. So, that would imply that alpha is in the intersection A intersection G, that would imply that A intersection Q, that would imply that alpha is indeed integer whose absolute value is less than 1. So, that from that we can conclude that alpha is 0. Okay. So, how are we going to do that? So, first to note that alpha already belongs to this the extension q omega n intersection A. So, why alpha is nothing but the sum of nth roots of unity divided by d, and this element is already in the extension, because all the nth roots of unity is going to be there in this extension. So, that should imply that alpha is there in this intersection. So, now let some sigma being an element of gamma. So, then if you calculate sigma of chi phi of g, so then you can see that this gives us exactly sigma of lambda 1 plus etcetera plus sigma of lambda d. So, now note that since lambda is are all some nth roots of unity, that would imply that sigma of lambda i's are also nth roots of unity. So, that means this sigma of chi phi of g, it is nothing but a sum of d number of nth roots of unity. Since lambda i's are not all of them are equal, that would imply that sigma of lambda i's are also not all of them equal. So, we have I j such that lambda I not equal to lambda j, that would imply sigma lambda I is also not equal to sigma lambda j for any sigma in gamma, because sigma is nothing but automorphism of q of omega I. So, that means the absolute value of this sigma chi phi of d is exactly strictly less than d, because this is going to be again the absolute value of this, since they are again sum of nth roots of unity. So, it cannot exactly reach the value d. So, that would actually imply the following. So, if I take this Q, which is exactly the product of sigma alpha, sigma and gamma. So, from our earlier observations, we know that this is belongs to Q intersection A. So, since alpha is in A and sigma of alpha again being a sum of nth roots of unity. So, this is also in A. So, that would imply the product is also in A. Now, since the product runs over all sigma and gamma, Q is fixed by all elements of gamma, that would imply that this Q is in the intersection. So, that means the absolute value of Q is exactly product of the absolute value of sigma of alpha, sigma and gamma, but we already noticed that the absolute value of this sigma of alpha is going to be strictly less than 1. So, that is concluded from this statement. So, that tells us that the absolute value of this is strictly less than 1. Now, note that this Q being element of this Q intersection A, which is exactly the set of integers. So, that would imply that Q is an integer and the absolute value of Q is strictly less than 1. So, that would immediately implies that Q must be 0. Since Q is 0, that would imply that there exists sigma in gamma such that sigma of alpha equal to 0. Now, since sigma being automorphism, so that would immediately imply that alpha is 0. So, this is what we wanted to prove. So, since alpha is nothing but chi phi of d, chi phi of g divided by d. So, this implies chi phi of g is 0. So, we assume that the phi g is not a scalar matrix. So, from that we conclude that chi phi of g is indeed equal to 0, and this completes the proof. Okay. So, with this actually we have completed the proof of Burnside's theorem. So, what I am going to do in the next class, I will introduce the tensor products, and then we will see how to construct G representations of tensor products, and using them actually, for example, we can get many already proved results like orthogonality and so on. And tensor product also gives us some important construction of representation in a way, like whatever interesting representation that actually that we want to classify and so on, that will actually come from the tensor products. Okay, I will stop here.